Okay, so first law of thermodynamics. And this is really short, so we're going to dive right into lecture 56 just as soon as I finish this one. So, first law. The laws of thermodynamics. These are observations of chemical reactions and the energy changes associated with them. Okay. Remember, facts are just, lots and lots of points of data. Laws are the trends that we see in that data. Okay. So, there are actually 4 laws of thermodynamics: the first, the second, the third, and the 0th laws. Thermodynamics, thermochemistry. Thermo means that we're studying heat, the transfer of thermal energy, so that we can understand when and why chemical reactions take place. It's a whole branch of physical chemistry, where physical chemistry is more or less the physics of chemistry. Okay, so the first law of thermodynamics. It can be stated in a lot of different ways. All the laws of thermodynamics can be stated in different ways. But the first law is about the conservation of energy. Okay? So energy is neither created nor destroyed. It can only change form. Another way is to say that the internal energy of an isolated system is constant. If a system is isolated, that means that no energy can go in or out. So that's why the energy has to be constant. Because energy can't be created or destroyed. So if no energy is going in or out, then it's just however much energy is in there is the total amount of energy in there. The ultimate isolated system would be the universe. It is no energy can go in or out because it's kind of all there is. So the total energy of the universe would be constant. To put it another way, delta E equals 0, or the change in energy is 0. Okay? But only for an isolated system. Okay? If the system is isolated, then no energy is in or out, so delta E, the change in energy, is 0, because energy can be neither created nor destroyed. Okay? So that is the first law of thermodynamics. Fairly simple to state most of the time, but it can have some far-reaching consequences. A big task in physical chemistry is very often finding a way to isolate a system or to identify an isolated system so that we can get that delta E equals 0. It makes it a lot easier to do lots of different kinds of math if one side of the equation is 0. Okay. So that is what we use the first law of thermodynamics for. Okay. That's how we take advantage of it. So that's all for the first law. Okay. Really quick, really easy, really short. Energy is neither created nor destroyed. Therefore, isolated system, delta E equals 0. Now let's dive into 56. State versus path functions. So a state function is a property that only depends on where you are right now, whereas a path function is a property that depends not just on where you are, but on how you got there. So the state function only depends on the current state of the system. Okay? So, like every year, the president gives the State of the Union address. He's talking about how things are right now. So a path function depends on the path you followed to get there. That's why they're called what they are. So an example of a state function versus a path function, we're talking distance versus displacement. Okay? So you start at a certain location, you travel 4 miles south, 5 miles east, 10 miles north, 8 miles west, and then 6 miles south. How far are you from where you started? How far have you traveled? Now let's go ahead and take advantage of my super fancy setup. So you start here, you travel 4 miles south, 5 miles east, 10 miles north, 8 miles west, and 6 miles south. How far are you from where you've started? Well, that's just this distance right here. 3 miles. You're 3 miles west of where you started. Okay. But the total distance you've traveled is this entire path. Okay. 4 plus 5 plus 10 plus 8 plus 16. That's going to be a total of 33 miles. Okay. So displacement, distance from where you started, your displacement is a state function. It doesn't matter what path you followed. However far you are from where you started is however far you are from where you started. If you traveled this really complex path, then you're 3 miles from where you started. If you just go 3 miles west, then you're still just 3 miles from where you started. Okay. But the distance you traveled, that is the path function. Okay. If you travel a different path, you're going to travel a different total distance. Okay. So that's the difference between a state function and a path function. Some physical properties don't care about the path you follow to get from A to B. Other properties do. In Lab 12, you have already encountered a state function in the form of enthalpy. Okay. That's why we're able to use Hess's law. We'll get to that next week, probably. Sorry about that. All right. Let's dive back into the lecture slides. So, some examples of state functions. Temperature, volume, pressure, mass, energy, and like I said, displacement. None of those care about how you get from A to B. The temperature of your system is whatever temperature it is. Volume, pressure, mass, energy, displacement. None of them are concerned with how you got from state A to state B. All they care about is what the state is. Okay. So we like state functions because you don't have to worry about measuring the path. But sometimes you can't easily measure a state function. Energy is the big one there. It is very difficult to measure energy directly. In fact, kind of impossible. Not entirely, but most largely, it's very difficult. Okay, so we often have to work with path functions, things where we do worry about what the path we followed was to get from A to B. Okay, so work, heat, distance traveled. The distance we traveled was the one we just talked about, where you followed a path and you travel a certain total distance. Huzzah. Work and heat are the two big things we're going to worry about next. What is work? What is heat? And how do we calculate them? Those are the sort of core doodads of physical chemistry. So let's consider a battery hooked up to a fan, using just a wire. Okay. All right. Going back to my super fancy drawing program. Here is our battery. And we have it hooked up to a fan. And over here we have a battery. That's just hooked up to a wire. In each case, the battery will use the exact same amount of energy. It doesn't matter to the battery what it's hooked up to. The amount of chemical energy, that lithium paste stored inside the battery is however much energy it has. It will expend all of that energy. So either way, the battery has a certain total amount of energy. But the battery is hooked up to either a fan on the left or to nothing on the right. Okay, so on the right, it will expend all of its chemical energy as heat. Heat is represented with a lowercase q. Okay, so the energy of the battery, the electrons travel across the wire. They meet some resistance inside that wire, and the wire gets hot. Okay, all of the energy of the battery is kind of just wasted as that heat energy. Over here on the left, though, it's still going to lose some energy as heat, but it's also going to do some work along the way. Okay. The fan that it's hooked up to is going to do something. Okay. So it's the same total amount of energy being expended by the battery, but along the way, it's doing different things. The electrons are following a different path to get from one terminal of the battery to the other. So heat and work are path functions. But energy is a state function. Okay? The total amount of energy stored in the battery is the same regardless, but the heat and work done as the battery releases that energy, those are path functions. So, like I said, a lot of physical chemistry is about finding an isolated system. A lot of it is also trying to find the path that we're looking at. Okay. Sometimes we have to worry about following the path, but sometimes, as much as possible, we try to eliminate that so that all we have to worry about is the state of the function, because state functions are easier to measure. Oops, come on. All right. So state functions are good. We like state functions because they're simple. You measure the beginning, you measure the end, you don't have to worry about what's going on in the middle. It makes it a hell of a lot easier. The problem is that, as I said, energy is difficult to measure. It's a distant sort of concept. It's locked away behind, a paywall. It's hard to get to. Okay? So we're often stuck with path functions. And path functions are nasty because in order to measure the path function, you have to measure the entire path. And in a way, that is kind of impossible. Okay? When you're talking about the distance you walk, if you stick to straight lines, if you really, even that is technically not perfect. But when you're talking about a chemical reaction and you're trying to measure the amount of heat going in and out of the system along the way, just the very idea of it is hideous and awful. And we really don't like it. So a good chunk of thermochemistry, of physical chemistry, in fact, is finding ways to be incredibly clever so that we can get the best of both worlds. Trying to get the thing that's easy to measure, namely the physical property of the path function, and turn it into a state function so that we only have to take 2 measurements rather than a nice perfect set of measurements along the entire path. Because if a path function is a state function, super duper easy all around. All right, and with that, we have finished this set of slides. Let's go ahead and give it another 5 minutes. Come back at 2:50, and we'll continue with system versus surroundings. Once again, I'll wait for questions.